Hello. In this video lecture, we will go over the basic elements of matrix algebra used uh, in the remainder of this course. These slides are courtesy of Professor Ryan Yu, but the content is mostly from the Rencher book, Methods of Multivariate Analysis. Okay, chapter 2. So why do we care about matrix algebra? Um, because the data is in matrix format to begin with. And here we will review the uh, needed matrix tools, and this is not going to be a complete review of linear algebra, but it is going to be sufficiently self-contained so that those with no previous exposure um, would not need any other reference. Okay. All right. Why matrix? A matrix is a rectangular or square array of numbers or variables arranged in rows and columns. Multivariate data is analyzed in a matrix format. And we typically use an uppercase boldface letter to represent matrix. Like here, A. It's a uppercase boldface letter, used A to represent this matrix. Now, let's look at an example. We have the ACT score and we have the college GPA of 3 students. Evan, Annie, and Jeff, the ACT and the GPA. And how can we represent this data in a matrix format? By writing A equals these two brackets. So we have 2 columns and 3 rows. Each column contains observation for a variable. So we have 2 variables, ACT and GPA. So column 1, variable 1, ACT. Column 2, variable 2, GPA. And then each row contains observations for a subject. And we have 3 subjects here, Evan, Annie, and Jeff. So the generic notation for the matrix above in this format, where we have a double subscript notation, A11. The first subscript indicates the row, the second identifies the column. First row, first column. Second row, first column. Third row, first column. And so on and so forth. So just to repeat, a matrix is a rectangular or square array of numbers or variables arranged in rows and columns. a notation that's been used. This is just a notation. A equals parentheses A subscript I and J, where A, I, J is the entry of the ith row, jth column. And typically, the way we structure data, and this is something that we will repeatedly refer to, we have n rows, so I goes from 1 to n, and we have p columns. So coming back to here, what is n here? N is 3, p is 2. Okay. So, and for such a matrix, the dimension is n by p, number of rows by number of columns. Two matrices, they are here. Two matrices are equal if they are the same size and the elements in corresponding positions are equal. So elements in corresponding positions means Aij equals Bij, and the dimensions are the same. For example, A cannot be equal to B because A is a 2 by 3 matrix, but B is a 3 by 2 matrix. But C and D are equal because they have the same dimension and the corresponding elements are, well, actually they are not equal because they have the same dimension, but the corresponding elements are not equal. D 2, 3. This is D 2, 3. Second row, third column is not equal to C 2, 3. Second row, third column. Transpose of A. If you have a matrix, then we can apply an operation called transpose, and it's denoted by A prime. Sometimes you also see A T. So instead of this prime, you see a T. Okay, so it's just a notation. And the transpose of a matrix A, denoted by A transpose, is obtained from A by interchanging rows and columns. Okay, so let's look at an example. So A is a 2 by 3 matrix, so A transpose will be a 3 by 2 matrix. So -5 will remain -5, but then this 3 replaces the place of 2, and 4 comes in the bottom. So if A is 2 by 3, A transpose is 3 by 2. Here's another example. B is a 2 by 2 matrix, so its transpose will be also 2 by 2. Now for a square matrix, the transpose, the diagonal, these are called the diagonal elements. 2 and 1 are called the diagonal elements. They remain the same. It's the off diagonal which switch location. And then if you have a vector, A here is a vector. What is a vector? A vector is a matrix with a single column or row. So this has a single column, therefore we call it a vector. We could also call it a column vector. The transpose of a column vector becomes a row vector. So A transpose here is a row vector, A is a column vector. Geometrically, a vector with p elements, here we have 3 elements, identifies a point in a p-dimensional space. So in a 3-dimensional space, this vector identifies a point in a 3-dimensional space. And the elements are the coordinates. The first coordinate, second coordinate, third coordinate. Now, as humans, we only experience 3-dimensional spaces. But in statistics, in data mining, in machine learning, in data analysis, we typically, and especially these days, or the last 20 years, we deal with data which are more than 3-dimensional, maybe 10,000 dimensional. And even though it is impossible for us to imagine a point in a 10,000 dimensional space, nevertheless, the vector with p elements, whether p wants to be 10,000, identifies in a 10,000 dimensional space. Okay. We call a matrix symmetric. When do we call a matrix symmetric? When A is equal A transpose. And that only happens if A is square. I mean, it doesn't happen for every square matrix. So it's a necessity for the matrix to be square, for it to be symmetric, but it's not sufficient. So if the transpose of a matrix is the same as the original matrix, the matrix is said to be symmetric. Let's look at an example. Here we have a matrix, it's square, and it's symmetric. Essentially what it means is that off diagonal terms, so everything along the diagonal is symmetric. So you have 4 on 4, you have 7, -7, and -7, you have -2 and -2. That's what we call by symmetric. And as I said before, regardless, the transpose of a transpose is always the matrix itself. So if you transpose a matrix twice, you get the same matrix. We talked about the vector. I will repeat it again. A matrix with a single column or row is denoted by A, so lowercase. We use lowercase for vectors, uppercase for matrices. And we always, it's default, we assume that A is a column vector, so A transpose is a row vector. Let's look at an example. Here we have a column vector. It has 4 elements. Typically, the way we represent it is that we have this lowercase letter, for example x, and then the elements will be just first element x1, second element x2, x3, x4, and then the transpose will be a row vector, x1, x2, x3, x4. Finally, we have a scalar, which is a single real number. A scalar is a single real number, and it's not bold. We can think of a scalar as a one-dimensional vector. Also, that's also something you can think of. Vector. Okay, so these are some basic concepts that we needed to get out of the way. I'm sure most of you have already seen them to some extent, but just to make sure everybody is on the same page, I will cover everything so then we can move forward without much difficulty.